Hello, I'm Robert Walker, and I plan to submit this paper to the astrobiology journals in spring 2021. And this graphic shows the outline. NASA planned to return a sample to Earth unsterilized by 2031. And in order to do that, they plan to construct a sample return facility. You might think there's plenty of time by the analogy of the Apollo mission, which returned a sample to Earth within 7 years of Kennedy's speech. However, there was no legal process. The sample return was done under the very weak Outer Space Treaty, which has a single sentence about preventing adverse changes to the environment of Earth. There was no peer review. The guidelines were published on the date of launch of Apollo, and it has never been legally tested. The legality of it is not clear. NASA, for instance, had no authority to quarantine the astronauts. They did that under the authority of the Surgeon General as an individual, and the legality of that is not tested, for one thing. The legal situation is much more complex today with environmental laws to protect Earth's biosphere. The quarantine wouldn't have protected Earth at all anyway. To start with, the Earth was probably contaminated right away. As the capsule was descending through the atmosphere, they vented some of the air, and the Apollo mission found that the lunar dust was very, very fine, and they could smell it. It smelled like gunpowder. It was just suspended in the air. So when they vented the capsule during the descent, some of the dust, pretty certainly, got into the ocean from there. Then when the capsule landed on the sea, then Navy frogmen came, got the astronauts out in a dinghy in the open sea, and the astronauts opened the capsule door, and at that point, for sure, dust from inside would have got into the ocean. And after that, it was largely symbolic. The quarantine, of course, was not tested, and this will come up with a Mars sample return. They would have to look at that legally too. Because with the Apollo mission, in one incident with Apollo 12 in 1962, then as a result of a cut in a glove, 11 technicians had to be quarantined. Carl Sagan observed that there was no basis really for the 14-day quarantine period. Leprosy has a latency period measured in decades. There are other issues with quarantine which haven't been mentioned in the planetary protection literature. In particular, a symptomless super spreader, the equivalent of typhoid Mary, could have Martian life in their microbiome, which is completely harmless to them through some genetic quirk. And yet, whenever they leave the facility, even if it's decades later, then they would spread it to other humans. There's no way to quarantine against that. You also can't quarantine against the return of, for instance, mirror life from Mars. Since the 2012, which is the most recent review of a sample return process, there's been a great deal of exploration of synthetic biology, and they now can see the way, though it's a very long process and very difficult, but they're making the first steps towards creating a synthetic mirror-life cell. The synthetic biologists warn us that if synthetic mirror life developed in a laboratory, which somehow also developed the ability to eat terrestrial organics, then the situation is not pretty at all. This absolutely must not be permitted to leave the facility, and the probability levels you have for a biosafety laboratory, they wouldn't apply to mirror life, because you couldn't take the risk of even one cell, even a 1 in a million chance of one cell leaving your facility. Then many synthetic biologists would say you shouldn't permit that. Because if the mirror life leaves your laboratory, and if it can metabolize terrestrial organics, it will gradually convert terrestrial organics to mirror life, to mirror organics, throughout the terrestrial biospheres, throughout the terrestrial biosphere, throughout the microbiomes. It will be slowly evolving and converting terrestrial organics to mirror organics, and most terrestrial life can't metabolize mirror organics. Just a few microbes, some species in Antarctica for instance, can metabolize mirror life. We don't know why Earth doesn't have mirror life. It's entirely possible that Mars does have it, and it has both kinds of life. When astrobiologists design instruments to send to Mars to search for life in situ, then they make no assumptions about what kind of biology would be there. They don't assume that's related to Earth life, because the hypothesis of transfer via meteorites has not been established. And even many life forms on Earth, of course, could not get to Mars, or could not get from Mars to Earth. And even microbes that could live there, such as for instance the blue-green algae Cucurbitiopsis, then it's one of our best candidates for terrestrial life that could survive on Mars, and it would not withstand the instant shock, the sudden acceleration from nothing of rock being ejected from the Mars surface. Some microbes can withstand that, but Cucurbitiopsis would not be able to. And then on re-entry to Earth's atmosphere would also be the fireball of exit. There's a fireball of exit from Mars, and the fireball of entry to Earth. Then photosynthetic life on the outside, or even if it's in a crack and getting partial shades, getting some light coming in, it would not survive that either. In the case of Apollo, it was soon shown that the Moon is sterile. But at the time of the Apollo mission, this was not proven. Carl Sagan had worked out that it was possible for a liquid layer to exist on the lunar subsurface if it was protected from evaporating, and if it was at just the right depth, if it was just the right warmth, and he thought there was a possibility that those organics survived at that depth from the early solar system, from the formation of the Moon. So it was a realistic possibility that there could be life in the sample. We later discovered that this liquid layer did not exist. And so that's when they decided it's safe to return these samples from the Moon without doing any precautions. However, in the case of Mars, we already have indirect detection of liquid water on Mars. Curiosity has discovered brines that form at night. There's the 100% humidity of the Martian atmosphere. Of course, there's no atmosphere on the Moon, so there's no humidity at night. But there's 100% humidity at night on Mars because it gets so cold. At times it gets so cold that dry ice forms on the surface. In winter, liquid water forms at night in the first 0 to 5 centimeters, detected indirectly but very robust measurements through the humidity, and in the sand dunes. Whenever Curiosity goes over sand dunes, it gets this signature, this signal of liquid water at night. And although it's dried out by daytime and you can never observe it, it's on the surface when it's at night, and there's just below the dust there would be some liquid water there. And it's too cold for terrestrial life, so as far as forward contamination doesn't seem to be a major risk. But there could be Martian life, might be able to survive there through using chaotropic agents which enable it to metabolize faster at very low temperatures, and then it could retain the water from the night into daytime in biofilms. And Viking has intriguing that both Viking landers, the labeled release experiment, then they show, after reanalyzing the data, Joseph Miller found that there are what look very like circadian rhythms with an offset against the highest temperature of 2 hours. But 10 minutes, tens of minutes could be explained by unusual chemistry. 2 hours is very difficult to explain. And it's also smoothed in a way you wouldn't expect from chemistry, but you would expect from life. And also, as well as that, when these samples kept dark for several months, that inactivated whatever was in the dust, which is again very difficult to understand with chemistry. So there might be life in the region, and just even in Jezero crater, where Perseverance will land. And then, if there is life on Mars, it has not been returned to Earth. If it's in this dust on salty layers. We have meteorites from Mars, but they come from 3 meters below the surface, which is considered to be likely to be sterile over pretty much the entire surface of Mars. The actual process of ejecting it into space would not send material from the surface of an asteroid impact. It sends it from below the surface. And any dust and salts would be incinerated as they left Mars, if they did manage to get into orbit, which is very unlikely. And of course, when we enter to Earth, there's that whole thing about if you had a blue-green algae, it wouldn't survive anyway. So we can't assume there could be life on Mars. We can't assume it's the same as terrestrial life. And some astrobiologists are very skeptical of life on Mars, and they argue that there could have been life very early on, but then it became a swan-song biosphere where it's barely habitable, and then it's just so close to being uninhabitable, it's hard to see how it could remain like that all the way through for 3 billion years. And I have a new suggestion there. The idea is that just as in the case of Earth, photosynthetic life prevents Earth from getting too warm. But actually, it's not optimal. If Earth was a little bit warmer, it would actually have more biomass. In the case of Mars, I suggest that the result is very suboptimal for the life. That as soon, and this would work on a very wide range of Mars-like planets, depending if it's similar to Mars, and even if it produces much more CO2 or less CO2, over very wide ranges of emissions of volcanic eruptions and the emissions of carbon dioxide into the atmosphere. As soon as liquid water forms on the surface in the form of rivers and lakes and so on, and if it developed photosynthesis at some time in the past, the photosynthetic life would spread across the surface, it would draw down the CO2, and this process would end when it reached the triple point of water, which is the status of the Mars atmosphere right now. This process has been suggested before using abiotic photosynthesis. I just crossed the A off there and suggested what about biotic photosynthesis. And that would be a way there could be life on the surface of Mars, and it'd be barely habitable and very, very hard to fight. And the amount of life would depend on the amount of CO2 emitted. So if there's quite a lot emitted, we would probably get closer to having a little bit of liquid water before it gets too much, the atmosphere gets too thick and the surface conditions get too warm. And if there's very little CO2, there would be just a tiny amount of life, but it would still be clinging on billions of years later, because if there wasn't any life, there would be lots of water. And that's the basic insight. So the life would keep it well below the optimal habitat, very suboptimal. If that's the case, then the sample returned from Mars might very well have life in it, and it may well have mirror life. So, and the mirror life would be evolved to be able to metabolize terrestrial organics, because it would be able to make it. First of all, there's vast amounts of organics come from space, interplanetary dust, comets, and meteorites, and that is of both-handedness. And then as well, if the both forms of life on Mars, they'd evolve to be able to eat each other. This, if that is true, then we don't know if there's mirror life in the sample until we study it. So until we know what's in it, we should assume that there's mirror life in it. So now, if you go back to the timeline for the return to Mars, and then as well people think, oh yes, so another thing, that as well as mirror life affecting our biosphere, there's also the possible of harm to human beings. So that's what the sample studies have previously mainly focused on. And they look at the possibility of something like Legionnaire's disease, which is a pathogen of biofilms, which is also an opportunistic pathogen for human lungs, which closely resemble biofilms. In the actual case of Legionnaire's disease, it's a pathogen of amoeba, but there could be, and it actually attacks the white blood cells, which reproduces inside them, which resemble a large amoeba to Legionnaire's disease. But there could be other ways that it be other pathogens of Martian biofilms which invade the human lungs, and to them it just resembles a large biofilm. And then if you also look at, there could also be opportunistic fungi, opportunistic pathogens of for your sinuses, for instance, and those kill vulnerable people on Earth. Opportunistic fungi. And one of those pathogenic fungi actually is a candidate to be able to survive on Mars. And then Joshua Lederberg, he remarked that we don't know. He raised this issue that the terrestrial biology is not adapted to recognize extraterrestrial life, and if it's never been challenged by extraterrestrial life, then would it have evolved anything to protect itself against it? And for instance, our epithelium protects against terrestrial microbes. He didn't say this is me kind of elaborating, but it's just quite a short sentence, just a few paragraphs. But for instance, our epithelium is protected by broad-spectrum antibiotics, and this is the first line of defense that keeps out a lot of microbes from in our skin and lining, all the linings of our lungs and so on. Then these would have no effect on extraterrestrial biology. It's very finely tuned to the terrestrial biology. And then the rest of the immune system might just not recognize it. We have an example like that with nanoplastics. Nanoplastics, well, they are organics in a way, and the nanoplastics are not recognized by the immune system, and even microplastics as well. So microplastics, even up to 10 microns, have access to all the human organs. The human body is essentially permeable to microplastics, but we don't have enough to be a really serious issue. However, that would mean that, especially for large amounts of extraterrestrial life in the habitat, for instance, if you're a Martian astronaut on the Martian surface as well, then if the Martian life gets into your habitat and spreads, and there's lots of it, your body would soon be full of these Martian microbes, and then they would all the organs would go everywhere, and then they would develop these blood halos, that happens with nanoplastics, but there would be far more if there were literally billions of these Martian microbes coming into your body, and those stick together in experiments with microplastics, and then it would cause blood clots. And as you can imagine, the many other serious possibilities. We just can't assume that Martian life is safe for humans. So, and then if it ever got into human microbiome, then mirror life. How could you sterilize a human of mirror life if it happened to be that it wasn't harmful to us? Of course, Martian life needn't be harmful at all. We have the archaea in the entire realm, entire domain of life that has almost no pathogenic effect on humans or other forms of life. So it's possible that whatever it is on Mars, even if it's a different biology, that it might have no harmful effect or very little harmful effect. Maybe, like the archaea are involved in tooth decay, so there might be minor effects. But we just don't know what is in it and what effect it would have on the terrestrial biosphere until we study it. And we can't study it if it's before it's returned, if it's returned uncivilized. So that basically is the outline of some of the main points in my paper. And then, so if we go and look at the sample receiving facilities, then the ESF study in 2012, they said they looked at starvation-limited microbes, and they found that this was a discovery in 3 years before, since the previous study in 2009, that starvation-limited life can pass through a 0.1 micron nanopore. And they also worked out that that's about the minimum of what is possible with terrestrial biology. So they required that release of a single particle of 0.05 microns is not acceptable under any circumstances. So I looked into what our technology is like today, and we don't have the technology to do that. The HEPA and ULPA filters are not tested down to that level, and there's an experimental filter for the virus that causes SARS-CoV-2, which goes down to 0.06 microns, and this is not available commercially, and this is able to filter out 88% of particles in that size range. So the technology doesn't exist to fulfill the requirements of the ESF study, that of 0.05 microns can't be released under any circumstances. So before NASA can start the build of the sample receiving facility, they first of all have to develop the technology. But they also have to do a review, because of the dramatic reduction from 0.25 to 0.05 microns in just 3 years, they said that a periodic review is needed. And also the discovery of gene transfer agents at 0.03 microns can transfer antibiotic resistance to unrelated archaea, unrelated microbes in the sea overnight. So there has to be some care even below the 0.05 microns level. Since then, I think a new review would look at synthetic biology and mirror life for sure. And it would also look at this, at the possibility of early life. Modern life can't arise in one go. If you look at the way the cell works, then you have the DNA, and it uses enzymes to translate that into messenger RNA, and they use the ribosomes to make proteins. The ribosomes and the enzymes, the ribosomes themselves have a protein subunits which are made using ribosomal RNA, which needs to be translated from the DNA, as well as the protein subunits, which are created using ribosomes from messenger RNA. And the whole thing is so looped together, and it all requires things that have already been made before by the DNA, RNA, and by the ribosomes. So there's no way that could just arise in some way from non-living chemicals. It's totally impossible, because everything needs to exist before the rest can exist. The early life must have been much simpler, and an estimate, for instance, it could have been only had the RNA, no proteins, and some enzymes, and a ribozyme instead of a ribosome to do the translation. It's a much simpler molecule, just made of RNA fragments. And the whole thing is much smaller, much more compact. And starvation-limited RNA world life would probably pass through a 0.02 micron filter. and the requirement would likely be that it should be a particle larger than 0.01 microns is not acceptable under any circumstances, and that 5-fold reduction is a huge challenge again. Every time there would be another 5-fold reduction, like the similar one. I think that's not impossible. And they would come to that conclusion by reviewing the research into early life, which has also been an awful lot in the last 8 years. And there's been so much research in synthetic biology, as I just mentioned, Hachimoji DNA, which is 4 extra nucleotides. So, and that is inheritable, and it's able to create an enzyme that leads to spinach fluorescing, brightly fluorescing. And the way that they protect Earth from mirror life, from synthetic biology, these experiments, and from mirror life, when we eventually make it, is to ensure that its biology is dependent on chemicals that you can only find in the laboratory. But we are, of course, not the designers of Martian life, so we can't use that method to keep Earth safe. So my proposal is, well, first of all, the simplest possible solution is for NASA to just return the sample sterilized. I suggest using X-ray nano emitters, which only have a power consumption of watts. And this then could be used to sterilize it during the journey back. We would need to design the Earth return orbiter and probably the sample capsule as well. The sample return capsule to be transparent, and then X-rays emitters within the orbiter. And then the orbiter, which is uses electrical propulsion, and that could come back and can come back to Earth and it'd be sterilized by the time it gets here. And then it would just do aero capture, and you wouldn't have to do this third mission. So it saves one entire mission. That would reduce the cost quite a lot. You don't need to build a receiving facility, and that would save $500 million for the facility, and it would save a huge amount for that mission as well. So that would be a big saving if they just decide to sterilize it. The Martian, it's very unlikely. Astrobiologists don't expect that the sample will solve any questions about whether there was past life on Mars, because past life on Mars would be degraded by, first of all, it's probably been warm at some point since it was deposited, so it would lose its chirality signature over tens of millions of years. And Earth life, that ancient life on Earth has lost, ancient organics on Earth have lost their chirality signature. Then it would also, it's only preserves it if it's been kept cold ever since. Which some samples would have been, but how do you discover whether the sample you're returning has got that signature? But there's much more than that. The perchlorates and the hydrogen peroxide are very degrading of the organics. And then most of the organics from Mars comes from the terrestrial infall, like I mentioned, the extraterrestrial, the Martian, extra-Martian infall, whatever you call it, the interplanetary dust, the comets, and the asteroid impacts, and abiotic processes on Mars. And then as well as that, in the early life, 3 billion years ago, it may well not have developed photosynthesis, and it could be very localized in both time and space. So the only real way of having, and also the Martian meteorites that we already have multiple simultaneous biosignatures, most of which could not be detected by Perseverance. The distant meteorite and the ALH 84001 meteorite, they both have multiple biosignatures, and most of them Perseverance couldn't detect. The most interesting of all our Martian meteorites. So it'd be quite hard for Perseverance to even return meteorites as interesting as the ones we have already. Perhaps if it returns lots of samples with organics, some of them will be at that level of interest. But to go beyond, because there is multiple biosignatures, do not mean that we've got life, because they can be mimicked. And so astrobiologists say that we have to send the instruments to Mars, and they've designed miniature. They could have sent, instead of sending MOXIE Perseverance could have sent half a dozen miniaturized astrobiological instruments, experimental instruments, for the same mass. That's the MOXIE is the one that's for colonization enthusiasts, which is just making oxygen, of no interest, no scientific interest. And so Perseverance is not searching in situ. It has no way to detect life in situ. That's what astrobiologists say that you need to do, and it needs to be able to home in bit by bit and say, oh, this looks like life, or this kind of rock looks interesting. How can we find, like, getting warmer and warmer, try and find, get down to the best samples you have of that. Once you find, you've got to be able to find the signatures in situ, or you could return 1 million samples and you never home in on the region where there could be life preserved from the past. You've got to be able to search for it in situ to have a chance. Or you're just randomly picking up random rocks and you've no idea if there's life in it or not. And that's good. That would take decades to find life that way, if it is very localized and hard to find. So we don't expect to have early life from Mars. It'll be of great interest to the geologists, it'll be of some interest to the astrobiologists, but the thing is, they think geologically the design of this mission. They think what matters is to have the context. We've got the astrobiological interest of the Martian meteorites, but we don't have the context. That's how geologists think. It doesn't matter which particular rock. You're looking for the context all the time. Now, context matters for astrobiology, but if you don't know if there's life in it, then the context is of no interest, or not much interest. It's not going to teach you much. If you're returning a sample that doesn't have life in it, it doesn't matter how much context you have if there's no life in it, or you can't prove that there's life in it. So for astrobiologists, this is just a technology demo mainly, and return some samples that may possibly be of similar interest to the Martian meteorites we already have. Might even be of less interest than the most interesting Martian meteorites. So in terms of astrobiology, if it's just past life, then sterilizing doesn't matter. But if it is present day life, then sterilizing, it would still be recognizable, but it would not, it would still be recognizable as being life if it was present day life, because there would be the chirality, there would be large molecules like chlorophyll, there would be the structure of the cell that you can see, and things like that, even if it's sterilized. And the sterilization that does not harm the geology. It only does minor changes, like changes in the colour of salt crystals to blue and quartz crystals to brown. You can live with that. The interspatial distances, the radioisotope dating and so on is not affected. So that's one solution. The other solution is to return to a safe place above GEO. I suggest the ring plane above geostationary Earth orbit. The ring plane is where Earth would have a ring system if it did have rings. Technically it's called the Laplace plane. It's not actually a plane, it curves. It's equatorial near to Earth, and it curves up to the plane of the ecliptic in a distance. And the geostationary Earth orbit, it's angled at an angle of about 7 degrees. Then a study that I found about optimal places for the graveyard orbit for geostationary Earth orbit satellites said that the Laplace plane is the best place to put them, because any materials that get broken off, including insulation and so on, insulation just wearing off because it degenerates on the sunlight, then these high area to mass ratio particles, they would still be confined within the ring plane, and it turns out that they're confined very tightly in the phase space of the inclination and the angle of the ascending node. And then eccentricity is also well defined as well, and they find that it wouldn't impact into the geostationary Earth orbit satellites. So I suggest that's an optimal place, and perhaps double the height of geostationary Earth orbit to keep well away from any future developments. And then from that position it would be very low latency from Earth. And then essentially we send these miniature instruments that I told you about to geostationary Earth orbit. So those will be the first ever tests of these instruments. And so in order to make it much more interesting for astrobiologists, I suggest we adapt a proposal by the astrobiologist Chris McKay. He suggested that as far as astrobiology is concerned, then the most interesting, a very simple sample return mission could be just as interesting as all this. His suggestion is that you have a lander that lands on the surface of Mars. Basically, the ESA-FETCH rover could do it by itself, without anything else. It lands on Mars, and it has a Mars ascent vehicle, just like it will have. It then digs up some dirt and puts that into the Mars ascent vehicle and sends that back to Earth. And that would, especially now with this reanalysis of the Viking results and the possibility that there was life there, then we want to know, even if it's unusual chemistry, we want to know what is there, both to be able to understand what Viking spotted, and then as well as that, for designing our own experiments to send to Mars. If there is a very unusual biochemistry that looks like that, which has this, looks like a chirality, like a circadian rhythm, but it isn't a circadian rhythm, then again we need to know what it actually is. And then if we do something like the labeled release in the future, then we will have a much better design, which will then be able to find life and not be confused by this thing that looks like a circadian rhythm and isn't. And the geologists should be interested in the dirt as well, and especially also in the dust from the dust storms, because these are like miniature geological samples from the entire surface of Mars, because the dust storms go global, and a dust particle can get from anywhere in Mars to anywhere. So it's really a treasure trove of miniature geological samples, and they may well find interesting things just by gathering some of the dust. As far as I know, Perseverance is just focused on drilling rocks. They then seal samples, and I don't think they have a way of returning dust except by accident. I suggest that the ESA-FETCH rover, that they try and persuade the geologists that will be of interest, especially of interest also for geology, to have a couple of samples of dust. And the samples tubes could have a magnet in the bottom, and then put those vertically on the surface of Mars when the ESA-FETCH rover lands there. Because this has been shown that whenever you have magnets on the surface in a rover, then you get the dust piles up above it on the outside when it falls. You get a thick layer of dust, and a region just away from the magnet there isn't any dust. So if we had a couple of sample tubes sitting next to each other, or even different places at different times, and they have magnets at the bottom built into them, then dust should fall into them, preferentially. And then the dust it's also of interest for human colonization, that the dust is likely to be it's liable to perchlorates, which turn into chlorates, which could be quite hazardous to humans. They could even make us go unconscious if you had a large amount of perchlorates coming to you, of chlorates coming to you as you're breathing. You really need to know what's in the Martian dust. And then in the forward direction, we need to know, there's some suggestion that it could be sterilizing to terrestrial life and reduce the possibility of forward contamination. But on the other hand, for instance at night and in the dust storms, when it's very thick layers of dust blocking out the sun, there wouldn't be any UV to activate the perchlorates. And so it'd be very interesting to have samples of dust, both in the forward direction, for different times and different seasons during dust storms, not in dust storms. And then this might, if there is a Martian life, it would have to be very abundant for this to be a possibility. But if there is Martian life, then it could well propagate in the dust storms. And so we might, just if we're very lucky, we might get a spore of microbial life if it's very abundant there. And it's not impossible it is very abundant, because we don't have any similar habitat on Earth with these layers of liquid brines widespread throughout Mars. just thin layers in the perchlorates. We don't have those perchlorates, and we don't have the 100% humidity at night thing. So even in like the Antarctic dry valleys, we don't have anything resembling its habitat. And it's not impossible, it's quite productive. After all, both of the Viking landers, if it was life they discovered, then they just dug a sample of the nearby dust and immediately found life. So it could be there's life almost everywhere in equatorial regions. Nothing we've sent there since Viking would be able to detect a layer of life just below the dust, with quite a high spore count, quite a high microbial cell count. So if we look at it like that, then there could well be quite good, then it could well be that we could return life. Then I suggest that we return the sample to above geostationary Earth orbit in this ring plane, and because they've got electropropulsion on the Earth return orbiter, then this would mean that they can target, they could for instance target going back. There's a very neat way of coming back without getting anywhere near Earth, and that might be optimal in terms of planetary protection. First of all, it's described the other way around. It's easier to describe the other way around. If you place a spacecraft in the close to the Earth-Moon L2 position, the point of equilibrium just beyond the Moon, of the Earth and Moon's gravity imbalance. If it's just beyond that, it will gradually spiral out and go further and further away in larger and larger halo like that. So it starts up like that, larger and larger and larger, and faster. And then, if you time it just right, then you can get it to go to the position of the Sun-Earth L2 position, and again be spiraling out there, go beyond that at just the right moment. Then it'll start spiraling out on that as well, get more boost from that, and that greatly reduces the delta V from Earth to Mars. Coming back, then as Earth return orbiter, it could then target the Sun-Earth L2 halo, and then the Earth-Moon L2 halo, and that would greatly reduce the amount of fuel needed to get back to above geostationary Earth orbit. And then hence in L2, then you go to L1, then you can do fancy things with the three body system of Earth, Moon, Sun, and reduce the delta V further and eventually get back to above geostationary Earth orbit. So that I suggest is something we do with very minimal modification of the mission they're already planning. And then you would study it by telepresence. You would send all these marvellous instruments, miniaturized instruments, to above geostationary Earth orbit to study the sample. You would immediately sterilize part of it. As soon as it gets there, you would cut off half all the rock samples and a small amount of the dust. And I didn't explain. Yes, so the way that I suggested we modify ESA-Fetch rover so it returns dust as well as the rocks is just to put it on top of the samples in the sample return capsule. We modify the arm that is going to pick up samples from pick up the sample tubes and add a scoop to it so it can scoop up some dust as well. And you do that last of all. You put all the samples in, and then you put in the 2 samples of the dust, and then you might put a plate on top of it, or you might just pick up the dust and just put it directly on top so it falls down between the tubes. Either way, you scoop up some of the dust from the surface and put it in the capsule just before you seal it. Then you close the capsule and the rest is just as before. So quite a small modification to the ESA-Fetch rover, which I think would greatly increase the astrobiological interest and might even mean that it returns life. If Viking found life in both locations, and ESA-Fetch rover is a rover, it can actually move around and decide where it's going to dig, then there's a very, very high chance that the ESA-Fetch rover returns life. And in that case, it's worth all the extra palaver to return it to geostationary Earth orbit, and then study it in situ with these marvellous instruments. And you don't need to build the sample return facility, save $500 million on that. You only build what's needed as you come across it. And if what we return is mirror life, then I think most people would agree that we shouldn't return it to Earth. We don't have the technology yet. And so I think that NASA really, they shouldn't even start on the legal process, because if my analysis is correct. So first of all, and you might say, well, maybe. So maybe you have some questions about all this, but so I'm just going to look at also about the original timeline, which is the first thing I look at in the paper. So they would definitely need the legal process, which didn't exist at the time of Apollo. And that would now be 8 or 9 years, and that's for in the United States. The parallel legal process would also be needed with ESA in EU, Canada and UK law. And then there would be international organisations that get involved, the World Health Organization for the quarantine of the technicians and effect on human health if it is leased from the laboratory. Then there would be agriculture and fisheries, anything to do with food and fishing. If you start thinking about large-scale effects though, and if that is accepted, that's a possibility, like mirror life, then almost any aspect of human life would be affected by that. So in that case, it's almost impossible to know where the legal process would stop. It's very hard to imagine such a legal process, especially if it once gets to large-scale effects, to be completed in 9 years. And then you have the facility, then because of all the lapses and mistakes with Apollo, then there's a minimum of 11 years once you work out what we have to do, and also that the technology doesn't exist. So you've got to add, this is an estimate in the paper which assumes that the technology does exist. But given that it doesn't exist, then we have to add an extra few years, first of all to do the review of the capabilities, then to develop the technology. And then the thing is that NASA is the proponent in the legal process. So NASA don't know until the end of the legal process whether their proposal is going to be accepted, whether it could be modified, or whether, using this argument such as about mirror life, the final decision is, no, we don't have the technology yet to do what you're proposing to do. NASA can't start the build of the sample return facility until it knows what it has to build. This is an actual requirement, that if it's going to cost more than $1 million, and that would cost about $500 million, then they have to do an enterprise service review and an enterprise architecture review. They have to know what to build, and they have to know how they're going to service it. And they won't know that until the end of the legal process. So they both have to be end-to-end. And if you just add the 9 years to 11, 8 years to 11 years, and starting 2021 you get 2040. But given how much longer both of those would be, there'd be extra years because you haven't got the technology yet, and you need the technology, and you need to know what you've got to build before you start the legal process. And then you've got to build at the end of that, and the legal process would surely take much longer once you talk about the possibility of mirror life. It's hard really to see how it could be returned before 2050. So that's why, just no matter how optimistic you are about all this, it's very hard to see it returning by 2031. It's in fact impossible. And I would say it's impossible, even if 90% of what I've said is in some way wrong, it's impossible to return it by 2040 either. So I think NASA would be well advised just not to try to do it this way. And they can do it by sterilising it or by returning above geostationary Earth orbit. They won't need any more legal process. In that situation, it's just the same as their return of samples from comets or asteroids, and they could complete that in the time frame by 2031. They would have sterilised samples that they can use immediately. They would have the unsterilised sample in orbit. And then if they decide that it isn't any life in the sample, it's not of major present-day astrobiological life interest, they sterilise the entire sample, return it to Earth, and it's pretty much the same as what they're already budgeting for. And it's the same budget as just sending this extra thing up there to the Earth Return Orbiter, but that has to have I think, sterilised part of the sample and then return it. It's almost identical, but it's then got this extra possibility. You either sterilise the entire sample or you leave it up there. And if there's mirror life there, it becomes the nucleus of an expanding facility for return of exobiology from anywhere in the solar system. And then finally I want to talk to end this talk by talking to the Mars colonization enthusiasts. And I should just say that oh yes, I didn't. And at the end of the result of the laboratory of the legal process, then even there's this phrase by Carl Sagan that we can't take even a small risk with 1 billion lives. And if we work through all this and the synthetic biology and the mirror life, then that's going to be, then there could well be an appreciable risk to 1 billion lives. And 1 in a million is a very small but appreciable risk. And the so that could well be that you'll get the prohibitory version of the Gaussian principle. I talk about that in my paper, and that would mean that you simply can't do it with current technology. It's just prohibited. Now, so for astronauts who want to prospective colonization of Mars, well, first of all, you will want to know that it's safe, because of all this possibility that suppose your body is just permeable to Martian life. You certainly want to know if that's the case before you land humans on Mars, and if it is, then what the life is going to do to your body once it gets into all the organs of your body. You certainly want to know the answer to that. And then, as well as that, if there is mirror life on Mars, there simply may be no way to return for an astronaut to return to Earth. It's very hard to see how, if the mirror life becomes part of your the human microbiome, how you could sterilize anyone of that. So again, that's something you want to know before you send humans there, whether they'd be able to return. And if we do discover mirror life on Mars, then I think that the likely outcome is we decide we're never going to send humans to the surface. It is the colonization enthusiasts, and I was a colonization enthusiast, I still am, in the sense that I really like the idea of humans in space, but I think we should focus on the Moon, not on Mars. And then, if there is life at this stage, it's much safer. It's just 2 days return. If you've got a medical emergency, you get back to Earth in 2 days. And there's a possibility of commercial value from the Moon. And then they use the analogy of humans, of the colonization of the Americas. But the Americas used exactly the same technology as you could use in the United Kingdom, you could use in the Americas, or in Spain, whatever. And the same method, you could just put seeds in the soil, and there even were humans already in the Americas, of course. And it's nothing like the situation of Mars, where the technology doesn't even exist yet to live there. The technology that we would need to live on the surface of Mars, it'd be much easier to live in the Sahara Desert with just using seawater. That'd be far, far, far easier. And also to live on the seabed, on the continental seabed, far easier. So Mars is not really of agricultural interest. You only have the agriculture because you're there for some other reason. And it's the same with the Moon. You couldn't plant a seed on the Moon, you couldn't plant a seed on Mars. Maybe some lichens could survive there, but you can't have human colonies subsisting on lichens that live in the partial shade on Mars. And so I think actually, if you look at it carefully, and the grey of the Moon is actually better than the rusty surface of Mars, because iron is better when it's not rusted. It's more useful if it isn't rusted. So the rusty surface of Mars looks attractive, but the grey surface of the Moon is more practical. And the very hard vacuum there is of great interest for making. It's much better than the best vacuums we have in our laboratories for making chips and for making solar cells. It could, for instance, be that in the future the Moon is where you make spacecraft, because they're easier to launch into space. And the very hard vacuum on the Moon would be a very good place, make it a very good place for making new spacecraft and building them, once you've got a big settlement there. So the Moon has lots of interest in the near term. And then in the future, then if there is life on Mars, then you could have a colony using there'd be billions of dollars unlocked to study this Mars life, and you could have a colony using the Phobos and Deimos moons of Mars as materials to make your space settlements. And then these space settlements, and there's a wonderful orbit, the Hera orbit, which comes near the surface of Mars every day, twice a day, on the opposite side of Mars each time, and it's sun synchronous, it's logged, and then it zooms away past the ice caps, and then it goes back to Earth. It's a small planet in the distance. Then you come in again, and 12 hours later, the opposite side of Mars. It would be a spectacular place to be from orbit. And astronauts in the ISS, they don't get tired of being in the ISS. And if you do some more work, and I think artificial gravity would deal with all the problems of bone loss and so on, then you could have human beings in settlement around Mars, in this, studying it on the surface. It would be a fascinating place to live. And then you could study Mars by direct telepresence using avatars on the surface of Mars. Robotic avatars, teleoperated. And then you could just teleport basically from one avatar to another to anywhere on Mars, look at it close up, with much better vision than you would have with just human eyes. And without the need to have oxygen or anything to eat or anything, you just leap to another one, start off in an experiment, leave it doing it. Or if you're doing something commercial, then you could be just like one of these games, I forget the name, that game that you do from, you have settlements that you have lots of little characters that you tell them how to move and what to do. So it'd be a world like that game. You would have robots, avatars on the surface that could do commercial things as well. If you want to build things and export them into space using Mars Ascent vehicles, then you could do that as well, operated from space. So that'd be very interesting, and the Mars isn't really. This was an insight from Asimov, but I think he got from someone else earlier, of planetary chauvinism. It's not his original word, but the idea that planets are the best place to live when you explore into space. Planets are very inefficient. You have a vast amount of mass, and all it does is to create gravity. The entire depth of thousands of kilometers of mass, and all it does is to create gravity. It's of absolutely no use to us except as a source of gravity. And so you make much more efficient use of resources in space settlements, with spinning very, very slowly for artificial gravity. And so there's enough material for 1,000 times the land area of Earth, or the surface area of Mars, in just the asteroid belt alone. Never mind, if we go further out, and we could build space settlements right out to the Kuiper belt, using large thin film mirrors to collect light from the sun. So once you have that vision, and then if you want to look at places within our solar system, as the likes of Callisto in the Jupiter system, which is protected both from the radiation belts of Jupiter and the ionizing radiation from the sun and cosmic radiation. That's also somewhat protected. It's just from the solar storm, sorry, not the cosmic radiation, by the Jupiter's magnetic field. It's probably the lowest radiation space in the solar system. And then on the moon, you have and it's got ice, and it's got rocks, and it's got just about everything you want is in Callisto. It's far better than Europa, where you've got planetary protection issues. And then on the moon, you've got the peaks of eternal light, almost eternal light, which have sunlight 24/7, nearly year round, for solar power. No dust storms, of course. And it's almost constant temperature, quite low in temperature, and that is good because it makes heat radiation from the heat rejection from your settlement much easier. And the solar panel just needs to be vertical and slowly turning like that once every lunar month. It's very interesting in terms of a place to design a settlement. And then you have the vast lunar caves, which could be up to kilometers in diameter. Much larger than, theoretically, they can be much larger than on Mars, and far, far larger than on Earth. So, and the possible ice at the poles. Certainly for the first few thousand, tens of thousands, even 100,000 settlements, then the moon has plenty for it. And then you've got the commercial attraction of the tourism from Earth. And really, the only advantage of Mars over Earth, or the Moon, is that been there, done that. If it's been there, done that, then as soon as you've been to Mars, Mars becomes been there, done that. So we shouldn't rule out the Moon because we've already been there. That is a very illogical way of proceeding to say, well, we've been to the Moon, so we shouldn't settle it. That is not a good way to reason. We should look carefully at the Moon and see if it is a good place to settle, and I think, with a careful scrutiny, the Moon is a far better place than Mars, and that we've been to the Moon already should not count against it as a place for space settlement. And so I really think that we need to be in this together. We will work much better on this if we're in this together, if the space colonists and the astrobiologists and everyone else are together on this. And so, as I can see, as I've explained, if you accept what I've said, then if you're a space colonist, you will want to know about the life on Mars. You will want to protect Earth's biosphere. Who doesn't want to protect Earth's biosphere? The only reason people would say not to do that is because they don't believe this stuff. So now, I just want to encourage anyone who's listening to this, please look carefully at my paper. If there's anything, don't spare any blushes. If I've got anything wrong in this, please let me know. And so I put up a number of other videos like this, and I've streamlined it, and hopefully I've done it as fast as I possibly can. I've left out vast amounts, but I've covered the main points in this video. It's really quite hard to shorten it, and this is the shortest I've been able to get it for the whole thing. And so I'm very interested in comments. Please look, it's a long detailed paper. I'll put a link in the video description, and I'm interested in any question, any suggestions, questions, any mistakes I've made, anything like that. And I'm putting this up for some feedback. It's such a long, complicated, difficult paper, and I'm really quite at a bit at my wit's end how exactly to proceed. But I think I'm just going to try submitting the whole thing to an astrobiology journal, and then proceed from there. But before that, I want some feedback, and have I made any major mistakes in it? It seems almost incredible but I think NASA is in the mindset of thinking it's like Apollo, perhaps. I don't know. It's hard to know why, but it's a case of different disciplines not talking to each other. I think is mainly what's happening here, if I'm correct. So the synthetic biologists not talking to the people working on the sample return. The sample return people, then the people who are designing what look like on paper, like biosafety laboratories that would work, but they don't satisfy this requirement. It's got the limit to less than 0.1 microns. And there's a typo, and they think there's just a 1 in a million chance of being of 0.1 microns, but it's actually of being 0.05 microns. But it's just not the technology, and not knowing the technology doesn't exist, and so on. And it's just not acceptable under any circumstances. And you have these people who just haven't talked to each other. And I think that's the main way that I'm doing this, by being multidisciplinary. And when it comes to the legal process, then these people will be talking through the legal process, because they will declare an interest. Synthetic biologists will look at all this discussion that's going on and say, what are your views on how are you going to deal with mirror life? And all these things I'm talking about now will come up in the legal process. There's no way they don't. So so the main thing is if I've got this right, and are there any mistakes. So do you see anything that I've missed, anything I've got wrong? And very interested in feedback about this. And thanks for listening.